Awesome. Thank you, Katie, for the introduction. Hopefully you guys can hear me okay at the back. And maybe why you might be a little bit confused is because nowhere in that lovely introduction was there anything about feed manufacturing. So maybe you're a little bit confused about why I'm here talking about feed manufacturing. But really, I'm here as a representative of these lovely people on the slide here. So Dr. Jennifer Ellis is a member of the Sustainability Committee that Katie mentioned. And really, things like feed manufacturing are a really important piece of what we do for nutritional modeling. And that's really what I'm going to be talking to you about today, is just sort of taking you through kind of an anecdotal journey of how digitization can support the sustainability of the poultry sector, all the way from automation of feed manufacturing to decision support on the farm. And actually, I think this ties in really well with what our previous speakers talked about, as well as the speakers coming up after me. And we're focused on cutting edge, what's coming next, but the reality is that mathematical modeling has been around in the poultry sector for decades. It's been around for a really, really long time, but as we think of new concepts, new things that are becoming important in the industry, sustainability is obviously one of them. And so we can use and adapt our existing tools as the interests and the needs of the sector evolve. But these models have been around for a really long time for industry stakeholders like nutritionists, producers, and researchers, both in academia as well in industry, to essentially predict or forecast how animals or groups of animals respond to a given scenario, whether that's nutritional, environmental, or management related, or some combination thereof. But when we think about models and sustainability, oftentimes we think of mathematical models and we think about optimizing feeding programs or feed intake or nutrient utilization. But there are several important avenues that we can actually apply mathematical models for sustainability that are already being done, and then also sort of new avenues as we move forward in this new kind of digital age. But namely, we can use mathematical models to optimize feeding practices, which have downstream benefits for sustainability. We can also use models to minimize economic and resource waste. And a lot of models have nutrient excretion predictions available. So for example, predicting how much nitrogen or phosphorus is being excreted into the environment. And some of these concepts have been touched upon in the previous talks about all of the different components that are important in the life cycle of poultry related to sustainability. And when we think about sustainability and really any sort of mathematical modeling, these models can range from very, very, very simple to very, very complicated. We can make this as complicated as we want it to be. But some of you might be familiar with a table that looks like this. These are the IPCC coefficients, and they really kind of represent the simplest representation of how we can think about sustainability at an animal level. So you probably cannot read these numbers, and you do not need to, do not worry. But these are essentially coefficients for nitrogen excretion rate in kilograms of nitrogen per ton of animal mass for a variety of livestock species on the left-hand side of your screen there, poultry among them. But really what this is doing is it's boiling down sort of the nutrient excretion contributions of an animal to a single coefficient. So like we did our math exercise in the last presentation, you can do a similar math exercise and multiply out these coefficients to get a rough estimate. For example, nutrient excretion. These estimates also exist for things like greenhouse gas emissions, as well as other nutrients like phosphorus. But this is sort of the simplest representation that we can think about. And then we can get a little bit more complicated, and we can think about sort of linear or nonlinear empirical models. Typically, we might think of these things in terms of growth and production curves. You might be familiar with graphs that look like this, where we're forecasting body weights or composition or egg production over time. But we can also think about these and apply these in terms of sustainability. We can predict nutrient excretion, we can predict emissions, we can predict a lot of other things using these kind of empirical modeling approaches. Let's make it a little more complicated. You can see where this is going. So we can also have mechanistic models, which are mainly thought of in terms of nutrient utilization and feed intake, but what makes these models a little bit different is that they're really based on these causal pathways and this underlying biological knowledge. So what we're doing in these models is we're describing what happens in the system using those underlying biological processes. So for example, representing the growth of an animal, looking at how protein is deposited, how fat is deposited, how these nutrients flux in and out of the major composition pools. And because of this underlying biological knowledge, they're able to integrate much higher levels of complexity, and they're able to simulate a wide variety of scenarios. And this becomes really interesting when we think about sustainability, because there's a lot we can play with here in order to figure out the sustainability impacts. But although we typically think of these in terms of feed intake and nutrient utilization, I've got examples here of metabolism, of egg production, calcium, phosphorus dynamics. These models can also directly have benefits for sustainability as well, just through the virtue of optimizing feeding programs. And I am going to give an example from swine, so don't go get Colonel Sanders to come yell at me, but I want to give you this example through swine of how these models can actually be used to have correlated benefits for sustainability. So this is an example of a precision swine system that has been worked on over several years. And it was developed with the goal of optimizing sort of protein feeding to swine. And really that was the goal, is to optimize the feed intake and the protein. But what they also found is that there were these correlated benefits for key sustainability metrics. So for example, they found that just by optimizing the feeding program, there was a reduction in production costs, there was a reduction in nutrient intake and excretion, and there was a reduction in greenhouse gas emissions. So this just shows you that, even if we don't originally design a model for a sustainability goal per se, there can be correlated benefits just through improving and optimizing our feeding programs. Do you want to make it a little bit more complicated? I think we should. We can step back even more and look at the farm level, because yes, it's very important to look at the animal. The animal is a really important piece when we think about sustainability, but obviously, as our other speakers mentioned, and as we'll talk about, I think, in the future sessions, is that the animal is just one piece of the puzzle. There's other pieces of that farm environment that are important contributors to sustainability. So that's when we can get into farm-level modeling approaches that, yes, include the animal, but also have representations of the farm environment. So what does it take in terms of water, electricity to operate that barn? How is the manure managed? How is the nutrient flows in and out of the manure? What are the effects sort of in that farm unit? So we can sort of step back even more and have these varying levels of scope in our modeling approaches to have sort of different perspectives on sustainability. And then we can consider something like life cycle assessments, which are becoming more and more popular, especially in poultry science, but just in livestock in general. And this can be considered a bit of even a step farther back from a farm level model, because with life cycle analyses, we're able to capture that additional effect of time. So we can account for historical experiences in the production chain. We can cumulatively look at sustainability metrics across the whole production cycle. And typically you find the objective of these life cycle assessments is to evaluate that compilation of inputs to the system, outputs, and then potential environmental impacts across the production stage. And you might have seen these terms, cradle to grave, cradle to farm gate. I'll show you in a slide or two sort of what is meant by that. But one reason why I also want to highlight life cycle assessments is that there is actually a standardized methodology for conducting them. So they are becoming increasingly standardized because these assessments are being more and more used to inform things like policy, because they really take into account the entire production chain. And there are several, obviously, benefits or important niches for life cycle assessments. They are supporting sort of those environmental and sustainability assessments at sort of the governmental level or the advisory level. They can help establish baselines for production systems. And this third one is actually what I want to sit in for a little bit, and I'll show you some graphs on a later slide. But these life cycle assessments can be useful to identify hotspots for sustainability in the production chain. So looking at all of the modules within the production chain unit and trying to figure out, okay, what areas of concern or opportunity are there in the poultry production chain to improve sustainability? And I'll show you what I mean by that in a second. And typically you conduct a life cycle assessment in a similar fashion. So again, it is a standardized methodology. There is a standard set of steps, but one of the most important ones is actually the first, which is defining the goal and the scope. And this is because it's very important to consider the scope of the production chain that you're looking at when you conduct these assessments. Not all life cycle assessments start and end at the same point, and this obviously influences how we interpret those assessments. And then the second piece there is collecting sort of an inventory. So once you define the goal and the scope of your analysis, you obviously need to go through and take an inventory of the important inputs and outputs and emissions in those different systems. And then you can conduct your impact assessment and then make your conclusions and recommendations. And then, as we love to do in mathematical modeling, we go back and we do the whole thing again. We get our impact assessment, and then we're like, maybe we need to tweak something, maybe we didn't consider this, and then you can redo it again, and you might have a slightly different perspective. But this is what I mean why in life cycle assessments we need to be cognizant of the boundaries of the system that we're looking at. And you might not be able to read that tiny little text there. But for example, you could get a life cycle assessment that starts at crop production on the farm. So we start with growing the crops that ultimately we're going to use for feed processing at the factory, and then we're going to feed that to the animals on the farm. So this could be considered a cradle to farm gate life cycle analysis because we're really following the production cycle through to the farm gate value of the product, so that egg or that meat production, depending on what species you're talking about. We can also include sort of the slaughter and the packaging process. So what Dr. Keeper was talking about with water and those sorts of contributions, we can even take a life cycle analysis into that avenue. So we can consider water inputs for processing in the cycle as well. This could be considered sort of a cradle to grave life cycle analysis because we're following that production chain through all the way to the processing of the actual product. And we can step it out even further and actually include, okay, now that we've processed the product, what are the inputs in the retail sale of that product? What are the inputs and outputs of the restaurant and household consumption or waste management? And this is truly a grave to grave life cycle assessment. We're really following it through from growing the crops to ending back up in the waste management system. So you can see that there are an immense amount of opportunities with these sorts of analyses, but also needs to be very carefully considered the boundaries and what the most appropriate boundaries are for a given analysis, depending on the goal. This is a particular example in broiler chickens. So this is done by Ermias Kabrab in his group in 2016. And this is looking at the effect of phytase on a life cycle analysis. And so what they did is they defined the goals and the scope of their analysis. And you can see sort of the system encapsulated in that dotted line there. And across the top in those blue boxes, they've identified the various inputs to their system, so things like water, electricity, diesel, fertilizer, pesticides, emissions. So you can see that it gets very complex very, very quickly. And then within their analysis, there are components like the preparation of the enzyme, the transportation of the enzyme to the feed processing, preparing the feed, transporting the feed to the farm. It can get quite granular very, very quickly, but what comes out of this is essentially looking at sustainability measures to produce 1 ton of animal live weight is sort of your outcome that you're looking at. And this offers sort of a unique lens compared to just, experimental trials where, yes, we can look at the impact of particular enzymes on an individual animal or a group of animals. But this actually allows you to look at the effect of treatments on the life cycle of the production system, which I think is really important when we consider things like sustainability. Yes, it's nice to, conduct trials and look at individual impacts of certain treatments or certain factors. But when we really consider sustainability, this can be a useful tool to take a step back and, if we do this, this might help the animal, but what are the other associated impacts in the system? And this is what I mean here about identifying hotspots. So I've just selected a few of the common kind of outcomes from a life cycle analysis. So things like global warming potential, which is usually described in CO2 equivalents, acidification potential, eutrophication potential, and primary energy demand. And the different colors of these bars represent sort of the different parts of that life cycle. So what you can probably see is that in certain sustainability measures, there are different colors in the bars. The different colors have different sizes. So if I look at primary energy demand, I can see that feed production, for example, is a very large contributor there. If I look at things like acidification potential, I can see that the manure application is a significant contributor there. So it helps us sort of distill down the different parts of the production system that could be targets for improvement in terms of sustainability. But with anything, we have to consider when we interpret these results, what are we really looking at? And so obviously the results of a life cycle assessment are impacted by the boundaries you consider. So, when you're considering life cycle assessments and you want to look between studies, you have to make sure you're comparing apples to apples and not apples to oranges. So obviously, if you have a life cycle assessment that goes cradle to farm gate, and then you have one that really goes truly grave to grave, they might have different sustainability metrics and might be a little bit more difficult to compare, but they still offer unique and valid perspectives on the system as a whole. And then one thing to keep in mind too with these life cycle assessments is that we get very, very complicated very, very quickly. We're adding in things like diesel and electricity and processing and water. And sometimes what happens in these analyses is that we actually end up boiling the animal back down to those simpler coefficients that I mentioned at the beginning, so that those tables of sort of default nutrient excretion, oftentimes that's how the animal is represented in these sorts of models. So we sacrifice the granularity at the animal level to have more complexity and the system level. And so it's just an alternate approach, but there is work being done in this space to have more complicated animal representations as well in these sorts of analyses. And now I want to talk a little bit about where we are now, and I struggle with this word because it's not just now, we've been sort of in this space for a while now, but really what we're in is the age of digital agriculture, agriculture 4.0. So everything is becoming increasingly digitized. Everything is a sensor. Everything is an app. We have so much more access to data, perhaps, than we have in the past. And this is necessitating the need to evolve how we do things. And we can leverage these opportunities not only for optimizing production and nutrient utilization, but also for sustainability. And they've been doing this on the cropping side of things for quite a while now. So this is not incredibly new, but using GPS technology, big data, machine learning to optimize how fertilizer is applied in a field, for example, to reduce herbicide use, only applying it where it's needed, and those sorts of things. And the poultry sector is digitizing as well, and it's exponentially digitizing even more than it was before. Of course, poultry houses have had digital tools for quite a long time. You can control the environment of the house digitally and those sorts of things, but now we're getting even more creative, and there's even more opportunities for data generation in a poultry house. So we have new sensors and technologies, it seems like every single day, to automate and collect data. And there are ones even to detect like poultry stress, to aid in feed management, to look at things at the processing level. So all aspects of the production chain are becoming increasingly digitized. And one of my favorite examples is actually down there in the bottom right. I don't know if you can see it, but this was a fantastic study that looked at virtual reality in poultry houses. So what they did is they put the chickens in a virtual environment and showed them lovely scenes of an outdoor pasture and friends outside, and it was a really interesting study. So it really seems like we are really in a creative, innovative space, and it's sort of at the point of seeing what techniques actually stick. I'm not sure if VR chickens is the future, but it certainly is entertaining. And so because of all these new sensors and technologies, we have this onslaught of data. And so what we can call is a big data wave, really, and not just in poultry, but across animal agriculture. So this is characterized by just a huge volume of data, variable data. We're getting data from audio, we're getting data from video, we're getting images, and it's coming fast, and it's really volatile, and it can be quite vulnerable. And so because of that, we have to evolve sometimes our strategies for how we process and analyze this data, because sometimes our traditional modeling approaches just are not equipped to handle large volumes of data. So that's why there's been this adoption or encouragement of the use of machine learning, artificial intelligence, those sorts of things in our mathematical modeling approaches and in poultry systems as a whole. And some of these examples are mostly focused at the live bird level. So you can see that we're using machine learning techniques to identify behaviors. We're using them to identify diseases. But what I want to highlight here, and this is where the feed manufacturing stuff comes in, so I'm glad you stuck with me. I want to highlight a couple examples that go a little bit beyond the live bird. So I want to highlight the work of some of the colleagues in Dr. Jennifer Ellis's group. So I want to start with an example in the feed pelleting, feed processing sector, Dr. Jihao Yu. He's a postdoctoral fellow, and he's been working on applying machine learning to predict and optimize pellet quality. And I also want to highlight the work of a PhD student, Maureen Sahar. She's been working on model hybridization. So I've tried to emphasize as I go pros and cons of different approaches, but what if we don't have to have one or the other? What if we can actually combine approaches and get the best of both? So you might remember, see, I brought this handy graph back for you, is that the feed processing and feed production is one of the big drains on energy demand. So it's hugely influential in sustainability because it does take a lot of energy and a lot of resources to process feed. And this is generally held true across life cycle assessments in poultry. And so these feed mills are big data generators, and they're a big opportunity to improve sustainability. And also, when we consider feed manufacturing and pellet quality, if we produce a pellet that is not a good quality, that's going to impact efficiency at the animal level as well. So not only are there direct sustainability implications just at the energy level of processing feed, but also if we do not process feed well and we deliver a poor quality product to the animal, that can also impact animal efficiency. So the results can be twofold. So what Jihao wanted to do is figure out if we can predict pellet quality, so using the pellet durability index in a commercial feed mill setting using machine learning. And I'm going to go through this very quickly, but if you have questions, please reach out to myself or Jihao. But essentially, he collected a lot of data at the feed mill with the help of a lot of partners. And what he wanted to do is apply many different machine learning algorithms to see if he can predict the pellet quality and figure out what features were important in predicting pellet quality. So he collected a lot of variables related to the environment of the feed mill, feed formulation, and manufacturing parameters. And then he computed his machine learning algorithms. And I've just selected a snapshot of 4 of them. He ultimately did 12. And of course, you cannot read these graphs, but what you can take away from this is that these are called permutation importance graphs. So on the y-axis of each graph, you have the variables that appeared in each machine learning algorithm. And the length of those red bars tells you how important or how influential that factor was in the model in contributing towards pellet quality. And some interesting results that we found is that really a lot of it was driven by the external temperature, which could influence the cooling process of the pellet. And we also didn't find that fat, so the fat content of the mixture was important in predicting pellet quality. And this could be because this is what highlights one of the limitations of machine learning in that feed mills have fairly tight regulations on the amount of fat that goes into the mixture. And machine learning models are very data-driven. So if the model was never trained on variable or extreme observations of fat, it is not able to predict what happens in those scenarios, which is really interesting to consider and an interesting limitation of these approaches. And I just want to highlight that one of the focuses of this work was to make it as applied as possible. So this is actually, Jihao created a pellet durability index simulator where you can play with a bunch of the variables in the study and actually use it to predict PDI in an interfaced fashion. And then very quickly, there are avenues to hybridize models, so combining approaches, because we want to get the best of both worlds. Data-driven models are really useful for predicting and forecasting, but they lack the granularity and the variability in predicting different scenarios. And there are a variety of ways that you can consider model hybridization. So for example, you can use machine learning outputs as inputs to mechanistic models to kind of get you the best of both. You can also use mechanistic models to generate a wide variety of scenarios and use that to train your machine learning approaches. And in practice, we do find that putting these approaches together does offer benefits for the accuracy of the predictions. So this is all to say that the future looks like, we don't know what the future will look like, but really it may hinge on, we want to keep these big data streams going and we want to leverage the data that we do have. Historically, getting really good inputs for our models are hard. And this means that our predictions might be a little bit off. Whereas machine learning and data-driven approaches can be very precise, but they lack that what if, they lack that granularity. You're more limited in the factors that you can explore because they're just driven based on the data they've seen before. So to make better estimates for sustainability or nutrient utilization going forward, and to be really useful for decision making, there are avenues that we might need to pursue to capture the best of both worlds. So with that, I'll just wrap up in saying that mathematical models can be really useful and provide new insights into sustainability, and we can do this at a variety of different levels of scope. And we really want to capture and leverage the opportunities offered to us by Agriculture 4.0. And I'll thank my collaborators and partners, and then please see the QR code if you have any questions. I'll be happy to answer them. Thank you.